Good morning, everybody. We are having this unit, FEE 422, Telecommunications Electro-Acoustics B, which is the digital version of the one we had in the first semester. And this deals with initially digital modulation and then the steps that you take in order to go from analog to digital. Basically, in digital modulation, we have three types. You can either change the amplitude, or you can change the phase, or you can change the frequency, just as we had with the analog uh, system. As a matter of fact, you can see that amplitude modulation here is a special case of AM in analog. And the phase modulation here, which is phase shift keying, is a special case of frequency modulation. And likewise, phase shift keying is a special case of phase modulation. Um, the, the idea of shift keying is uh, an accident of history in the sense that in the early days, what used to happen was that the a human operator would actually change the frequencies by having a key in his or her hand and moving the key from one slot to another as one slot for one frequency. And then when the frequency is supposed to change, then they would move that key and move it to another slot. So when they're doing that, they would be said to be shifting the key. Uh, and so we have SK attached to the digital modulation options. We have this diagram here, which is basically indicating the types of digital modulation for ease of remembrance. You can now have variations of the three, and including even a combination. For example, you can have a combination of amplitude and phase in QAM, which some people call QAM, and you can also have other variations. But the main ideas, the main types are those three. In amplitude shift keying, what happens is that you can either have uh, an amplitude, let's say 5 volts, for the to indicate the presence of a binary 1, or no no amplitude to indicate the absence of, in other words, a 0. Usually, the amplitude is, of course, the amplitude of a carrier. So, for example, if the input data is indicated by DT here is this sequence 101101, we're indicating non-return to 0, meaning that the pulse representing a 1 does not return to 0 in the bit duration. It stays, if it's high, it stays high for the bit duration, and if it's low, it stays low for the bit duration. It does not return to 0. Yeah, yeah. Oh, um, and there's a small interruption. And so when you, if you had two amplitudes, A1 for a 1 and A0 for a 0, then this is what you would observe for this sequence that we have indicated here. Um, if you if A0 equals 0, then of course there'll be nothing where there's a 0, and there'll be a burst of a carrier where there's a 1. So so the 101101 would be represented like as shown here. For the case of the this amplitude shift key, or that if you have the on-off variety, where either you have a burst of a carrier and then no signal, a burst of a carrier, no signal, it's very easy to demodulate, because all you look for is the absence of presence of a carrier. It's very simple. The disadvantage is that it's susceptible to noise interference. Um, Noise usually affects only the amplitude. Therefore, uh, the amplitude shift key in general uh, is the one that is most affected by noise. This is applied in the transmission of data over optical fiber. When you go to uh, the other, okay, we're giving an example. The You can have this is in terms of representation. You can have an oscillator which is generating the carrier, and then the data signal, and then a multiplier that produces the result that you want. So in this example here, the first VDT is the data 10110, and VCT is the carrier. Then when you multiply the two, the the blue is the result, and diagrammatically we represent it this way. If you were to look at the amplitude shift keying in the frequency domain, you would find the data signal is low frequency, and then the carrier is over there. And when you multiply them, then you're going to get some shift in frequency. So the setup is you have the data signal at low frequency here, and then the carrier, when you multiply the two, you're going to move to some band of frequencies around FC, as shown here. What we have in the intervening part here is the mathematical expression that shows how we arrive at what we're showing in the diagram here. Frequency shift key. In frequency shift keying, the frequency is the one that is shifted by the message, and you could have more than two frequencies in principle, um, but we can understand the workings of frequency shift keying by considering two frequencies. Here again, uh, if you were to have two frequencies, you can think of the output signal as being some amplitude multiplying a carrier at frequency f1 for a binary zero, and the same thing multiplying a carrier with frequency f2 for binary 1. And so when you look at the diagram, if 1 is higher than the binary 1 is a higher frequency than the binary 0, uh, then what happens that you're going to see more cycles where there's a 1 and fewer cycles when there's a 0. So you can see the diagram is more spaced out where there's a 0 and closer together when there's a 1. Some people will call it mark and space. The mark for the presence of a 1 and a space for the presence of a 0. Again, that is from history. In the days of Morse code, what used to happen was that you would have a mark and then a space, and so the person transmitting the message, uh, such as would be the case for people at sea stranded and asking for help, you would find something that would go to space, space, and so on. So the idea came from there, and in some books you still find one represented by a mark and a zero by a space. How do you generate FSK? You have an oscillator at one frequency, another oscillator, another frequency, and a means of switching between the two frequencies controlled by the data. So we have an electronic switch, and then the modulating signal, which is providing the modulating data, controls the switch. So if there's a 1, you go to the position 1, and if there's a 0, position 2, and so on. So We then have the demodulation. We must be able to determine which of the two possible frequencies is present at a given time. The advantage is that the frequency shift keying is less susceptible to errors as compared to amplitude shift keying. The receiver looks for specific frequency changes over a number of intervals, so the voltage or noise spikes can be ignored. The disadvantage is that the spectrum is 2 times that of the amplitude shift key. Where is it applied? Over voice lines in high frequencies and radio transmission, etc. If you are trying to think to demodulate FSK, you can have a bandpass representation where you have what is called a matched filter. We'll talk about a matched filter later on. A matched filter centered at F2, matched filter centered at F1, followed by an envelope detector, There's a lot that is going on in this diagram here. You can see we're using an envelope detector, which is what we met in the analog domain to demodulate an amplitude modulated signal. So really what the matched filter at F2 and the matched filter at F1 are doing is to convert the frequency shifted signal to an amplitude modulated signal so that you can use an envelope detector. There's something here that some people would call a slicer. Basically, it's a decision device which will output a high value when the upper arm is greater than the lower arm, and a low value when the lower arm is greater. What you can see is that the Mach and space filters in the above figure are bandpass filters that are centered on the Mach frequency and the space frequency respectively. In the simplest form, the information bits from the FSK signal are demodulated by subtracting the amplitude, as I just said, in here. When the difference is greater than 0, a Mach is assumed to be present. And when the difference is less than 0, a space is assumed to be present. So the slicing idea is there in blue. If you want an unbiased slicer, then both filters are designed to have identical noise bandwidth so that one will not favor the other. You can also have these detectors operating at baseband. You see here the filter is centered at F2 and then another one centered at F1. So higher up in the band. If you want them to operate at baseband, then you have to shift the incoming signal first. So you have an oscillator tuned to the Mach frequency to shift the incoming signal, and then an oscillator tuned to the space frequency to shift the signal. So one arm is shifted by the Mach frequency, and one arm is shifted by the space frequency. Then the matched filter is now the same. This matched filter are identical, and the envelope detectors are identical. This is now operating at baseband. You can see from this diagram that it looks a little bit more complex, slightly more complex because of these multipliers at the beginning. But it is simpler in the sense that now everything can work at the baseband. You don't have to tune the filter to F1 and another one to F2. So again, we do the mathematical operations here that are giving us the relationship that we need. I think what we need to indicate here is that there's a parameter that we're calling the correlation coefficient, which is defined as given here. You have two signals, S1 and S2, with energies E1 and E2 respectively. The energies are defined there. And then the correlation coefficient is given here. We need that in order to be able to to detect their two signals. So if you have a frequency shift keying signal, two separate frequencies, then you'll find that if you the separation of the two frequencies is f1 and f2, f1 minus f2, relative to the bit duration. We represent that by parameter h. We're putting absolute value here so that it doesn't matter whether f2 is greater or f1 is greater. And the correlation coefficient will be given by sine 2 pi h over 2 pi h. The normally what happens when you do this integration that we had up here, you will get two values, the f1 plus f2 and f2 minus f1 or f1 minus f2. And we are saying here that you can either make f1 plus f2 to be an integer, or you can make f1 plus f2 to be very, very high compared to f2 minus f1. And so what then happens is that the term that matters is the one that comes from the different. And where we're going with this is that we get to the point where we talk about so-called minimum shift key. This is the signaling at the relationship. When the relationship between f1 and f2 is that h will be a half. Yeah, so h. So when you have minimum shift keying is occurs here when h is a half. That's the what is called orthogonal signaling at when the frequency spacing is a half relative to the signal duration. The correlation coefficient is 0 for several values of h, but you look for the minimum value, saying the smallest value of the modulation index h that gives orthogonal signaling, and that's called the minimum shift keying, which some people also call fast FSK. So some more examples. So now in terms of the diagram, if you're having FSK, then this is the data, the carrier, and then the resulting modulated signal down here. The binary phase shift key implementation is very similar to the one we had for FSK, incoming carrier, incoming data, oscillator, and then a multiplier. You can have quadrature PSK. Quadrature PSK is a way to put two signals on the same pair of carriers. You have on a pair of carriers, you have one carrier at 90 degrees phase shift relative to the other. So it's like using the same bandwidth, but you're having twice as much data transmitted. So in this case, we'll have a 2-to-1, a 1-to-2 converter. In other words, the data comes in a serial stream, and then you output them two at a time. So one part goes one way, the other part goes the other way, and you will then have multipliers by carriers 190 degrees out of phase with the other. So the bits then will be separated into pairs. So what will happen is that if what was coming is if the data was like this, you have 0, 0, 1, 0, 0, 1, 1, 1, if that was the data. Then we group them in pairs. So you have 0, 0 there, 1, 0, 0, 1, 1, 1. So of those pairs, pick the first one to come up here. So for example, the pink guys are 0 here, 1 there, 0 there, 1 there. Then the black guys will go down this one. The second black guy, this one down here, then this one down, and so on. So the red is one arm of the modulator, and then the other red, the other arm. And what you observe is the blue. The signal that you have here, this black is the current, and so on. So we have an example there that you can read for yourself and see. You can also think about the quadrature carrier as specifying a point in the signal space, so that you have the amplitude of the in-phase component on the horizontal axis and the amplitude of the quadrature component in the vertical axis. And then now we have a point here, and then the distance from the origin is then the length, the amplitude of the actual carrier. And this gives the idea of signal constellation. When you specify the signal points in a signal space, then what you have are called constellations. It's sort of borrowing the idea from the constellation of stars in space. So for example, if you have on-off signaling, then you have a point at 0 and a point at 1. Binary phase shift keying, a point at -1, a point at +1, and QPSK with those 4 points as indicated. Yeah. So the binary phase shift keying, you can think of a 1 as being mapped into signal S1 and the binary 0 signal S2. And in terms of mathematical forms, the signals are basically a carrier, a single carrier, a frequency FC, and the signal, the 0 is mapped onto the same carrier but shifted by pi radians. So it's, when you work it out, there's a negative sign that pops up. TB is the bit duration. FC is the carrier frequency, is chosen to be some integer multiple of the inverse carrier frequency, and the carrier frequency, you can either make this be an integer multiple of 1 over t, or you can make FC to be much larger than 1 over t. Either way, this is fine. The reason is that when you're trying to get the correlation coefficient, as we said earlier, the correlation coefficient would have 2 terms. You want to be able to retain one and ignore the other. And if you have the carrier frequency to be a multiple of an integer multiple of 1 over TB, or FC is much larger than 1 over TB, then you'll be able to have only one term. So you can also say that in binary phase shift keying, the pair of signals differ in phase by 180 degrees. So if you're thinking about the signal space representations for the binary phase shift keying, as we said, there is one signal at S1 on the positive side, and the signal S2 at the negative side. And you have to multiply with the square root of EB, which basically, as you can see there, that in the signal space you're going to have the basis signal phi1 given by this expression. And so S1 is the square root of EB multiplying phi1, and S2 is minus the square root of EB multiplying phi1. And so what then happens is that diagrammatically you can show them this way. There's only one basis signal phi1, and therefore we just have these things on the line. If now you transmit the two signals, one of the two signals, there could be noise, and noise could move what you transmit to a place which is different from where it was initially. And so you have to specify what we are calling a decision rule. Um, if the two signals are equally likely, then in other words, the probability that the signal S1 is transmitted is the same as the probability that the signal S2 is transmitted, and that equals to half. Then what you do is that you just set the decision threshold at 0. And so you say that anything you receive that is positive, you're going to declare as S1. And anything that is negative that you receive, you're going to declare as S2. If, of course, they were not 0, then you have decision somewhere else, the threshold somewhere else. And so what happens is that if, for example, transmitted uh, 1, which means this is the signal that you receive is indicated by the black uh, curve in terms of the probability. Then you make an error if you receive something on the negative side. So an error will occur when a 1 is transmitted if the signal that is received is, uh, is negative. And likewise, if a 0 was received, it was transmitted, then the signal will be as shown in red, and an error will be made if what is received is positive. So what we're saying then is that the probability of error is the probability that you have a positive when a negative was transmitted, or you have a negative when a positive was transmitted. And we have um, 0.5 times the probability that one of them was transmitted, and 0.5 times the probability that the other was transmitted. Each of them are the same. The probability of an error given as 1 is the same as the probability of an error given as 2. And so when you add these guys, the half and the half add up to 1. And so what you end up having is the probability of error is q times, is the q, not times, the q of the square root of 2ab over n0. We have indicated, we have explained what q is in head here. So this gives us the probability of error in BPSK. You can generate a BPSK as indicated here, input data and the spectrum shaping filter, and then we have a product modulator which gives you the binary wave. The receiver, initially you have a multiplier which shifts the signal down to the right frequency range, and followed by an integrator, and then there's a decision device. So it's a 1 if the threshold is exceeded, and a 0 otherwise. FSK, we handled this before. And, the signal space for FSK is given here. The explanation is that you have two basis functions, one at f1 and one at f2. And the S1 is given as EB times phi1, and S2 is EB times phi2, of course, is a square root. And the important thing with this FSK is that the signals are now not in the same line, but they're 90 degrees out of phase. And so the distance between them, D1, 2, is the square root of 2EB. So what is happening is that you draw the decision threshold to be this 45-degree line. And we're saying that anything above the line is with the message point S2, and anything below the line is with the message point S1. And the probability of error is now going to be a little bit large. When you go through the mathematics there, the probability of error is now q the square root of EB of n0. Previously, there was a 2 there. N0 is the underlying noise power density. If you want to think about what is called a coherent binary FSK receiver, this is what you got. You got phi 1 is the basic signal for the frequency the signal for frequency F2, and integrate and so on. We summarize here that if you have probability of error and as well as the distance between the two signals, binary phase shift keying, the distance is twice the square of EB, and the frequency shift keying distance is square root of 2EB, the 2 is inside, and amplitude shift keying also the 2 is inside. And the expressions for the probability of error are given there. We compare the results by plotting the signal to noise ratio on the horizontal axis and the probability of bit error on the vertical axis. And the amplitude shift keying and frequency shift keying are together in the green curve, whereas the binary phase shift keying is in the red, a little bit lower. You find that asymptotically, as you go to larger and larger signal noise ratio, the distance, the separation between the two curves is about 3 dB horizontal. So I think that's what we need to do for now. What follows here is a table of the Q function. It will help with the calculations of the signal to noise ratio. And we want to stop there at the moment. So